Thank you so much for giving me the opportunity to speak. My name is Jordan Kotler, and I'm going to tell you about quantum learning for quantum chaos. This is based off of two papers which are to appear, in particular this first paper in collaboration with Thomas Schuster and Masoud Mohseni. Let me begin with this quote by Richard Feynman in one of his famous talks about quantum computation. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." In this talk, we're going to explore different ways in which quantum algorithms inform our understanding of nature, in particular quantum chaos. There's different ways in which quantum algorithms help us understand nature, so let me list two of them. One of them is that quantum algorithms provide a language for understanding nature. They give a new way of conceptualizing known physical laws and provide a means to describe new physical laws which are otherwise inexpressible. Historically, the usual currency of the laws of physics has been energy, particles, and fields. But quantum information and quantum computation have provided, over the last 10 to 20 years, a new language with which to understand the physical laws and to help us and have helped us also uncover new laws which are otherwise inexpressible. Another way in which quantum algorithms help us understand nature is that they provide a tool for learning about nature, particularly a tool in the sense of experiments. They provide tools for scientific discovery as well as enable new kinds of experimental data. We can imagine that our experimental apparatus performs some kind of quantum algorithm or quantum computation in the way in which it interacts with the system in nature which we wish to investigate. And it allows us to, by running those algorithms, uncover properties of our physical system of interest and to analyze the experimental data, either using quantum post-processing on classical data or most optimistically in the future to do quantum information theoretic processing on quantum data. So in this talk, we're going to be focused on quantum learning algorithms for understanding properties of quantum chaos. We're going to explore how to use quantum learning algorithms to quantify and understand aspects of quantum chaos, in particular a diagnostic of quantum chaos, which I'll explain shortly, called the out-of-time order correlator. Now, many-body quantum chaos is a subject of intense recent study over the last 5 to 10 years. So the talk is going to be divided into 3 parts. In the first part, I'm going to provide a short review of quantum chaos and first classical chaos to lead into it. And I will introduce an object a mathematical object which diagnoses quantum chaos called the out-of-time order correlator, abbreviated as an OTOC. In the second part of the talk, I'll overview some experiments for measuring out-of-time order correlators, both experimental proposals as well as their instantiations. In the third part of the talk, I'll provide information theoretic bounds on learning these out-of-time order correlators. That is, I will explain how information theoretic bounds prevent us or limit our ability to learn certain features of quantum chaos about systems in nature. So let me begin with a review of quantum chaos. So let's start with classical chaos to begin with. Suppose that we have some dynamical system which starts with some initial condition, x naught, some initial point from which we evolve. If we evolve this forward, then we get some trajectory, here shown by this blue line. Now suppose that instead of starting from x naught, we perturb our initial condition by some amount delta x naught to give us a new initial condition, which we then can evolve forward in time, which gives us a different trajectory. We can see in this cartoon that the trajectories diverge. And in fact, in certain cases, the trajectories can diverge exponentially as a function of time. This kind of phenomena was initially studied in the late 19th century by Poincaré and Hadamard. Poincaré was particularly interested in the setting of the three-body problem in celestial mechanics. Now, the subject of classical chaos qualitatively changed with the advent of computers, of modern computers, in the mid-20th century. This enabled hands-on exploration of nonlinear systems, namely by simulating them on these computers, which allowed people to uncover new features and heralded a new golden age of the study of classical chaos. Now, of course, the reason why it was so that it took computers to have many of these observations is that simulating classically chaotic systems by hand is really difficult to do. It's extremely tedious, and people were not able to recognize some of these new features until they had a quick feedback loop by being able to interface with a classical computer. As a side note, I should say it's my hope that with the advent of quantum computation or full-fledged quantum computers or even quantum many-body simulators, we can have hopefully similar insights about quantum chaos by being able to have a tight feedback loop in our interface with the systems which simulate quantum many-body dynamics and exhibit interesting features of quantum chaos. But back to classical chaos, one famous example of these simulations was done by Lorentz when he was working on weather simulations in the 1960s and realized that if he changed the initial conditions of a simulation by a little bit, it would lead to drastically different behavior in the weather later on in the simulation. This is sometimes summarized in the somewhat whimsical butterfly effect. The idea being, if, say, a butterfly flaps its wings in Montana, it could lead to a tornado forming somewhere in Texas. Of course, this is an apocryphal statement, but nonetheless, it drives home the point that small changes in initial conditions can have an outsized effect in dynamics later on in time. Let's consider the case of a classical Hamiltonian system. For example, we consider a trajectory which has 3 position coordinates and 3 momentum coordinates. Suppose we want to understand how the first position coordinate is a function of time, namely x1 of t, how it changes as we perturb its initial condition, x1 at time 0. That is, let us take the derivative of the position of the first coordinate at time t with respect to its initial condition. In certain instances, we can get that this has an exponential growth, which is often referred to as Lyapunov growth, where this lambda is the Lyapunov exponent. Now, it's convenient to re-express this derivative in terms of a Poisson bracket, which is a standard part of classical Hamiltonian mechanics. Here, the Poisson bracket is between the particle's first coordinate at time t, as well as the particle's first momentum coordinate at time 0. And since these are equal, of course, this exhibits the same growth. The Poisson bracket is going to be particularly useful for us shortly when we generalize to quantum mechanics, because it bears a pretty straightforward quantum generalization. So let me now summarize the salient features of classical chaos, which will generalize to the quantum setting. As I said, we have a classical Hamiltonian, which induces dynamics on phase space. And we have that this Poisson bracket yields Lyapunov growth. It's measuring the sensitivity of the trajectories of the system at time t to perturbing the initial conditions. Now, in the quantum setting, we instead have a quantum Hamiltonian H, which acts on a Hilbert space. And we do is we upgrade the Poisson bracket via first quantization to the Dirac bracket. Here we have 1 over IH bar, as happens when you do first quantization. And the Dirac bracket is none other than the commutator between the Heisenberg evolved x1 and p1 at time 0. That is, these are operators. And when we write this operator as a function of t, I mean we evolve it forward by an amount t in the Heisenberg picture under the evolution of the Hamiltonian H. Now, on the left-hand side, in classical chaos, this object is a number, whereas this object is an operator. So if we would like to get a number out of it, well, we can take its expectation value with respect to some state rho. And if we do so in certain interesting cases, for instance, if rho is a thermal state, this can sometimes fluctuate around 0. If we're interested in its size, its magnitude, it's fruitful to square this quantity so that we're looking at the expectation value of a strictly positive quantity. If we do so, if we square it, we get -1 over h bar squared times this commutator squared, which can give rise to the Lyapunov growth. Here there is a factor of 2 on account of having squared this commutator. And this lambda is often referred to as the quantum Lyapunov exponent by analogy with the classical setting. Now, this means of generalization from classical chaos to quantum chaos of this particular quantity was originally developed by Larkin and Ovchinnikov in their paper in 1969 and was recently repopularized by Kataev in 2014. A particularly interesting application of a result rather about these kinds of correlators is due to Maldacena, Shanker, and Stanford in 2015, in which they established that certain classes of quantum many-body systems, for which you can generalize this, actually have a bound on how fast the Lyapunov growth can be. Let me now explain what is an out-of-time order correlator. It's related closely to this commutator squared, which I just explained to you. So let me write out this commutator squared. If I expand out the commutator squared, then one of the terms is going to be this. This is a correlator which is out of time order. The reason it's out of time order is that the insertions of our time the insertions of our operators are not monotonic in time. That is, we start at time 0, we go up to time t, we go back down to time 0, and then we go back up to time t, zigzagging in time. Now, this particular term then is called an out-of-time order correlator correspondingly. This correlator, in fact, contains the Lyapunov behavior that I claimed was in this term. So in other words, it suffices to compute the out-of-time order correlator to see the Lyapunov growth. Now, just to really drive home the point of why it's out of time order, here's a time axis. So suppose that we insert the P1 operator at time 0, then we insert the X1 operator at time t, we go down to time 0, and then we go back up to time t. So we see that it zigzags in time, and as such is out of time order. This is readily generalized to the context of quantum many-body systems in the following way. Suppose we have a lattice system. Here is a one-dimensional lattice of, say, qubit degrees of freedom. And we insert an operator V, say, on this lattice site at time 0, and we insert an operator W on this lattice site at time 0. Because they're on distinct lattice sites, they initially commute with one another. But if we evolve V in the Heisenberg picture, then the operator is going to spread out. And when it spreads out, it will eventually cover the site on which W was inserted. That is, at a later time, the Heisenberg evolved V may fail to commute with W at time 0. So in that setting, it's natural to consider an out-of-time order correlator in which we trace a state, some density matrix rho, against this commutator squared, a V of t against W at time 0. This can also exhibit Lyapunov growth, and is a natural quantum many-body generalization of the few-body version that I showed you on the previous slides. Now let's turn to experiments for measuring out-of-time order correlators. There have been a myriad of different experimental proposals and instantiations over the last 5 or so years. Here is a smattering of them, some sampling of them, and they have been constructed for a wide variety of systems, from quantum computers to NMR systems to cold atom arrays. And they rely on several different kinds of algorithms or mechanisms by which to extract an out-of-time order correlator from the measurement data. So let me summarize some motifs which are common to these different kinds of experimental protocols for measuring out-of-time order correlators. That is, they fall into several different themes, which I'd like to summarize. One is that many of the protocols require time reversal to be implemented. That is, they require not just evolving forwards in time, but backwards in time, often in an alternating fashion. Namely, you evolve forwards and backwards and forwards and backwards. Some of them do not require reversing the directionality of time, but do require quantum memories, which you can regard as quantum computers, or an ancillary system, which can be entangled with the main system of interest. And by virtue of the entanglement and the computation that you perform on the ancillary degrees of freedom, you can use that to extract out-of-time order correlators from the main system of interest, even though you don't have the ability to reverse its directionality of time directly. And finally, there are some protocols which do not require time reversal, namely in which the system of interest, the system in nature, whatever the system is that you're investigating, only evolves forward in time by its native dynamics. And these kinds of protocols instead rely on clever measurement schemes in order to extract the out-of-time order correlator. Let me start this in preparation for some conceptual remarks. Condition 3, this third motif, is most like the natural world. In the real world, or in natural systems, I should say, we cannot, in general, reverse time for most experimental systems. So if I give you some condensed matter system, give you a superconductor, if I give you a sheet of graphene, then you cannot readily reverse the directionality of time of its dynamics. More broadly, of course, we cannot readily reverse the directionality of time for the dynamics of our universe as a whole. Now, this should be juxtaposed with quantum simulators, and for which we can, of course, reverse the directionality of time. But the point is that, in particular, we cannot reverse time in conventional experiments with natural systems. In an ordinary experiment, we just simply cannot reverse the directionality of time of the system which we are investigating. So now let me turn to information theoretic bounds on learning out of time-ordered correlators. So here's the setup. Suppose that we have oracle access to some unitary dynamics. Phrased in a more simple way, suppose that we have some system which we're interested in studying, and we have the ability to just let it evolve by its native dynamics forwards in time. What's important is that we are only given the ability to evolve it forward in time. That is, we do not have the ability to reverse the directionality of time of its dynamics. The system could only evolve forward in time by its own dynamics. And for now, let's also assume that we don't have a full-fledged quantum computer, which can also be regarded as a quantum memory in which we could store quantum data. So we don't have the ability to store quantum data, much like conventional experiments, but otherwise we can perform an arbitrarily complicated adaptive experimental protocol in which we can measure our system of interest, we can let it evolve, we can make measurements again, and we can use previous measurements and the measurement outcomes, which we can process, to inform which future measurements we should make and how we should process the data which we get out of those. So our task is to compute some specified out-of-time ordered correlator to within constant error. So our result, one of our main results is as follows. Any time-ordered experimental protocol, that is an experimental protocol of the kind that I described, in which you can only evolve your system of interest forward in time, any time-ordered experimental protocol to determine an OTOC, an out-of-time ordered correlator to within constant error, must in some instances require accessing the time evolution exponentially many times. That is, there are some kinds of systems for which extracting the out-of-time ordered correlator, if you can only evolve the system forwards in time, is exponentially inefficient. So there are certain properties of quantum chaos which you cannot readily extract using any quantum learning algorithm from your system. Of course, a quantum learning algorithm with the constraints that I described, you don't, namely, you can only evolve it forward in time. You don't have the ability to store quantum data, which is true of contemporary experiments, essentially. In contrast, an out-of-time ordered experiment, namely one in which you can reverse the directionality of time, can determine any out-of-time ordered correlator to within constant error by accessing the time evolution only a constant number of times. That is to say, if you do have the ability to reverse the directionality of time, then you can actually extract the out-of-time ordered correlator. These results, built off of previous work in quantum learning theory, in particular, this hardness result builds off of previous work in quantum learning theory from these papers in 2021. Let me now make a chart to summarize some of the findings. Suppose that there's some out-of-time ordered correlator that we want to measure. In our work, we construct out-of-time ordered correlators for which any time-ordered experiment requires exponentially many operations or measurements or time evolutions, I should say, in order to measure the out-of-time ordered correlator to within constant error. Whereas if you have the ability to reverse the directionality of time, you can learn the out-of-time ordered correlator efficiently. What's also interesting is that for the examples that we study, if you have the ability to couple your experimental system to a quantum computer, you can also efficiently learn the out-of-time ordered correlator, even if you cannot reverse the directionality of time. This is very good because it means that there is hope in being able to measure certain of these quantities if you have a quantum computer, even in instances where without a quantum computer, you would not be able to measure it efficiently, given that you can only measure this, that you can only evolve the system forwards in time. So in this manner, quantum computers can help us uncover new properties of quantum chaos, which are otherwise inaccessible. Let me conclude with a brief discussion. We've established fundamental limits on experiments learning certain features of quantum chaos. We've identified limits on our ability to learn about the chaotic dynamics of systems in nature for which we cannot reverse time. This provides an example of a rich interplay between quantum algorithms and physics. By studying the fundamental limitations of quantum algorithms, which probe some phenomenon in nature, in our setting, features of quantum chaos, we can gain new insights into the phenomenon of quantum chaos itself. So thank you so much for your attention.